let's consider a system with a pulley, and the pulley is frictionless. Let's attach two objects of mass m1 to one side and of mass m2 to the other side, and there's no friction, so the string can just slide, and there's negligible mass in the string. And let's find the acceleration. Let's compare the two ways of doing this. So if we use ma equals f, then the constraint here between the two objects makes this a one-dimensional problem. And so we have to choose a convention. Right, we could do a free body diagram and derive the right-hand side by putting arrows indicating the tension force upwards on this one and m1g downwards, and we would have to choose a convention as to which is positive and which is negative. So say we do the gravitational force downward on this one is positive, so this would mean that counterclockwise acceleration would be positive and clockwise acceleration would be negative. The tension force on that one comes in as negative. And for the other one, we have m2 x double dot the acceleration of this object as minus m2g plus the tension. And so we combine these two equations, right? We add them together, as we know, to get that left-hand side. We get rid of the tensions, and we get m1 minus m2g. And so the acceleration is equal to that. So if m2 is greater than m1, we have a negative acceleration, which is compatible with clockwise. That would be a clockwise acceleration, which would come in negative given our convention. So now let's look at this from a Lagrangian perspective. So if we do that, we want kinetic and potential energies. Doesn't really matter where we choose our reference point, but let's say we decide that this is our reference point, so we need some way of figuring out the height. So let's say that from here to there is L, and therefore there is some, say, x value from there, from this object to here. So this is a point object. And therefore from there to this object, we have x. Right, so when this comes down, when this comes up to the top here, this one comes down to the bottom, and we have L, and so the distance from here to here would be L minus x. And so we need to write kinetic and potential energy. So the kinetic is just 1/2 m1 v1 squared plus m2 v2 squared, but given that there's only one v here, we can write that as m1 plus m2, and the v is just the x dot squared. And the potential energy is, let's find the heights. So the height of this one is L minus x. So we have m1g L minus x. plus m2g times x, and that's the total potential energy. In this choice of coordinates, we also have an acceleration clockwise that is negative and counterclockwise that is positive. When we take two derivatives of this, we get a minus x dot squared. So if we flip the way we choose the coordinates, then we change the convention there. So we have the same convention. So now we can build the Lagrangian, right, which is t minus u, and that gives us m1 plus m2, x dot squared over 2. We have a minus sign, so we can do plus m1g x minus L minus m2gx, and we can do now dl by dx, and that is m1g from this term, and then we have a minus m2g from this term, and we need to do d by dt of dl by dx dot, and that becomes, right, dl by dx dot gives us m1 plus m2 x dot, and when we take a time derivative of that, we get m1 plus m2 x double dot, and these two things have to equal each other, so we get m1 plus m2 x double dot equals this, which is m1 minus m2g, and so of course we end up at the same place.